We've talked previously about what happens when you compile a simple program consisting of an application containing a main function and one class, which is typically broken between a header containing the class definition and a code file implementing all of the class member functions. Here in Lecture 4, we're going to dive a little deeper into this process and investigate the three primary phases involved in compiling and linking a program. There are actually three phases of what we typically talk about as the compiling process. The first phase is something called the preprocessor. The preprocessor is the phase that's responsible for handing all of the so-called directives, that is, lines that start with a pound sign or sharp sign, like pound include and pound define that we saw one quick example of in the previous chapter. The preprocessor simply does substitution of some text for some other, typically more complex text. So what the preprocessor is doing is translating from human-readable source code, such as, for example, in a prog.cpp file that we're showing here on slide 3, into another human-readable form called the translation unit, in which all of the pound include and pound define and various other directives will have been processed, making changes to the human-readable code. Then that translation unit is taken by the compiler. Now, here we have a little confusion because we're talking about compiling overall, and we're saying that the compiler is one phase of compiling. The compiler is responsible for taking the translation unit, which is human-readable, and converting that into executable binary code in the form of an object file. So over here on slide 3, we're seeing that the compiler reads from the translation unit produced by the preprocessor and typically generates an object code file, a .obj file on Windows, or a .o file on various versions of Unix, including Mac. And then finally, the third phase of the compiling process typically involves a so-called linker that's responsible for hooking together the global variables and function calls that exist in the program's object file with the associated binary implementations of those functions pulled from various libraries and perhaps various other object files. The linker hooks all of these things in these separate binary files together to create a single executable file, which on slide 3 we're showing as prog.exe for a Windows box. On a Unix or Linux or Mac system, it would just be typically named prog. Okay, so we go from a human-readable file through the preprocessor to another human-readable file. That human-readable file is passed through the compiler to produce a binary object code file, and that binary object code file is then combined with various other binary object code files to produce a binary executable file. Now, the translation unit shown here on slide 3 is usually not saved on your disk. It's usually simply created in memory as an intermediate step between the output of the preprocessor and the input of the compiler. Let's take a little deeper look at what's going on with the preprocessor and the translation units. Now, we have used include directives in the past, and literally what an include directive does is to suck in an entire copy of typically a human-readable header file. Now, technically speaking, it's not required that that file be human-readable. It is possible to have these things called precompiled headers, but as a general thing, when you're working on your own code and you're developing your own headers, of course those headers are going to be human-readable. And when you say include myheader.h, what's going to happen is that that line, include myheader.h, is going to be replaced by an entire copy of that header file, myheader.h. That's going to be sucked in place of the include line, and the whole contents of that file is going to be part of what's passed on to the compiler. Probably the second most commonly used preprocessor directive after include is define, or pound define, which we took a very quick look at in the previous lecture. Basically, what pound define does is to define a token, that is a single word, to be replaced by some character sequence when that token is encountered later in your source code. And as I mentioned in this previous lecture, before we had the word const, it was #define that was used to define names for constant values. Here I have two examples on slide 5. I'm defining the token capital PI to be replaced by the sequence of characters 3.14159 blah 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 846. And I'm defining the token capital DIM to be replaced by the sequence of characters 1000. So below that in my source code, where I have double DA square bracket capital DIM close square bracket, well, that token capital DIM is replaced with 1000. And then continuing in the initialization part, we're initializing the array DA with pi. That is, the first element of DA will be the value given by the sequence of characters 3.1415926 blah 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 846. And also notice that we can use dim as the array dimension in for loops. #defines used to be everywhere in code before const was introduced. It's still common, but less common than it once was. A third very common kind of directive are the conditional compilation directives, such as #ifdef or #ifndef. Now, these conditional compilation directives allow you to either compile in or pass on to the compiler a certain block of text, or alternatively decline to pass along a certain block of text, depending on what #define statements the preprocessor has or has not encountered. So in this example here on slide 6, let's suppose that we include some header, defs.h, containing some definitions of things, some #defines of things. That line, include defs.h, will be replaced by the entire contents of the defs.h file. If in that defs.h file a #define of pi exists, when we get to this conditional compilation directive, #ifdef pi, since pi has been #defined, we will pass along to the compiler, that is, the preprocessor will pass along into the translation unit, this block of text consisting of cout insert double quote pi is defined as, etc. In fact, all of the lines up to but not including the #endif will be passed along into the translation unit. One detail I want to point out here is that pi, where it appears by itself in the cout statement, is a token, and so that token is replaced with the text 3.1415, etc. But pi in caps inside of a string is not a token in the same way that it would not be treated like a variable name or a function name. In that case, capital PI is simply part of the character string. So the preprocessor does recognize character string literals and will not do a substitution of a #defined manifest constant value. Below the ifdef directive, we have its opposite, ifndef. Ifndef means that you want to pass along to the translation unit certain code if that preprocessor token pi was not seen in a #define directive. Okay, so in other words, if we look at this entire example program on slide 6, we include the defs.h header, which sucks in an entire copy of that file, and then as the preprocessor continues reading the remainder of the code here, int main goes to the translation unit, open curly brace goes to the translation unit. Now, if pi was seen in a #define directive, the statement cout pi is defined as whatever is passed along to the translation unit, otherwise not. And then continuing on, if pi was not defined in a #define directive, the statement cout pi has not been defined is passed into the translation unit.